Exercise 58. So let F be a complete valuation field with respect to a discrete valuation, such that the residue field so let's denote OF is real integer, M is maximum ideal. Let's say small k of F, or small k just. It's residue field. Let's require this to be finite, and then the exercise asks you to show that the real integer of F is compact. So firstly, let me make some notations. So this is following my lecture notes, which is not quite talking about the local fields of number theory, but in more general sense, just representation theory of some P groups. So here, it's better to just clarify notations here. So firstly, so when we're talking about those valuations, so actually this is more standard notation, what is called valuation norm. So we can always keep in your mind the example of, so you're working with QP, you have the p-adic valuation, and that p-adic valuation gives you a p-adic norm, which is defined to be, take some real number bigger than 0, less than 1, and then you take its power as the valuation, p-adic valuation of x. And so up to normalization, you could think of this as taking exponential, and it comes back by taking logarithm, right? So we call this, usually we call this discrete norm, but that's what is called discrete valuation here, okay? So when we use this symbol, so as you could imagine, that's what we're really talking about. So moreover, so let me be more precise. Maybe let me just give you a slightly general setting. So we are talking about here just discrete valuation, not even require it to be non-Archimedean. So let me the definition. So let F be a field. But first, let's be more precise. What do we call it? Evaluation. So this is a map from F to non-negative real numbers, such that for any two elements we require firstly norm 0 equivalent to element equals 0, secondly it's multiplicative, lastly triangle equality. So we're not requiring it to be non-Archimedean yet, so following this definition, it is called discrete. If there exists some delta positive such that whenever you fall into a small neighborhood of 1, then your norm is exactly 1. So this seems slightly strange, because what is in our mind for a discrete norm would be the p-adic norm, but this is equivalent. So small some exercise show that this is equivalent to, say, the log of all the absolute value of all the valuation here called valuations of A is discrete. Subgroup of the additive group of real numbers. So this is what our intuition tells us, because as we say, once you take log, so just take an example of your PID evaluation, right? Log of x, PID evaluation, this is what? This is just by our definition. This is just PID evaluation up to a normalization. Right, so obviously this is discrete. Positive, additive group of real numbers. And then non-Archimedean. If it is valuation or it is equivalent So again, when we're talking about valuation, that's what I said, that's what in your common sense should be called a norm, such that it satisfies stronger inequality, triangle inequality, doesn't matter you write x minus y or x plus y, that's equal to the maximum. Okay. Otherwise it is called Archimedean. Archimedean evaluation. Yeah, I put the definition here because in this setting it's slightly different than the general. Although we don't care about setting, but you could think of it as interesting way to think about those things in a slightly more general way. Why? Because, so let's say that we could define what is called local fields in a slightly more general sense. So in our case, the local field would always be characteristic 0 case, finite extension of QP in the characteristic P case. There's those K double parenthesis T, finite extension. So comes from number 3 right here. Local field F. So non-discrete. Field F, which is locally compact. And is complete with respect to a non-trivial valuation. A remark about this kind of definition. So if we define to be so, then what are those possible local fields? So QP is non-Archimedean fields. And the theorem tells us that if f is complete with respect to an Archimedean evaluation, then there are not too many choices. F is isomorphic to real numbers or complex numbers, and the valuation will always be equivalent to the absolute value, or sometimes call it infinite. No. So this tells you that with local fields, when you're talking about non-Archimedean situations, just real number or complex numbers. And correspondingly, one could define for valuation field similarly for local field, defined in this case the valuation range, the maximum idea, the residue field. So let's put some exercise. The valuation is discrete if and only if it's maximum ideal, so which defined to be all those elements in this valuation field such that its norm smaller than 1. This is equivalent to this is principal. Which means in our common sense this is a DVR. Then in this case, if this is generated by pi, then we call this uniformizer, or in this general setting, sometimes people call it a prime element. And we know that for non-Archimedean, second sub-exercise, suppose f is complete, with non-Archimedean valuation, then the Cauchy sequence could be described very very easily. So suppose you have a series and with all those f converges if and only if just an goes to 0 itself for the topology induced from this valuation, call it metric or not. Right, so this is very quickly. We could even give a proof of this very shortly. Just talk about this Cauchy sequence. So take any integer n bigger than n, then just compute the finite sum from index for the indexes for the elements of index between n and n. And let's talk about its absolute value. Obviously, by the stronger triangle inequality, this should be less equal to the maximum of all those an. And then obviously this goes to 0 when you take m, or when you take this big n big enough. So this is a Cauchy sequence. It suffices, I mean, it suffices too. So this condition is obviously true, and when we showed it that just require this an has limit 0 will force this to be a Cauchy sequence. And so it's complete, means that it converges to a limit still in F, converges in F. So now let's go back to the proof of the exercise. So it's talking about something locally compact. Proof. So let's quickly recall. We want to prove that if F is a complete valuation field with discrete valuation, then the residue field is finite, implies the real integer is compact. So let's consider the metric induced by the valuation. This makes OF into metric space. And sub-exercise for metric spaces. Because we want to discuss when is this OF compact, we give one sufficient condition, which is residue field to be finite. but we use equivalent characterization, which is for matrix spaces, compactness is equivalent to sequential compactness. Which means that for any sequence you could find a subsequence that is convergent in your space. So now let's check. Start with a sequence in UF. It then suffices to prove that there exists a convergent subsequence. So let's denote a chosen or a fixed representative of the residue field, or more precisely, this is in OK, in OF, a fixed set of coset representative. For the residue field class. And then notice mod KF has cardinality finite, implying that this cardinality finite, right? And then we are going to use this to construct a convergent subsequence. What we are going to do is, let me write A0 into the form. So with help of our uniformizer pi, we could write any element uniquely into the form let's write a 0 plus a 1 pi plus a 2 pi square, etc. A 1, so you have a J form sequence, right? For each AJ, I can write it into the following form. Similarly, etc. Right? So what I'm going to do is first focus on this first column. Let's look at this as kind of a two-dimensional chart. Let's look at the first column. So I'm going to select from the AJ, infinity many AJ, first step, a subset or a subsequence, which means still infinity many terms. So what are those subsets? What are those subterms what are those AJ I'm going to select? It is that notice that there exists infinitely many aj0, so which means looking at this first column, among those terms there are infinitely many aj0 such that aj0 equals sum b0 comes from this representative set, because there is a finite set and all those aij, they comes from this. I could retain it uniquely in this form, right? Let's think about p-adic integers. In that example, this for qp, this is just 0, 1, 2p minus 1. You fix a representative set and then you express any elements in this completion, which is qp in that case. In this case is our f. p-adic complete field into such expression. So all those aij are in your curly A. And then because there are finite elements in A but infinitely many elements in the first column, there must exist infinitely many terms equal to the same one of A. And we select those ones. For example, this, let's suppose, so this four, of course there are infinitely many, just focus. Suppose all those A0, 0, A1, 0, A2, 0, A3, 0 equals B0, and there are more, but I just want to use this chart to visualize this. And then what I'm going to do, we preserve those ones, we eliminate those not selected in the first step, and then we look at the second step. Again, there exists infinitely many aj1 such that now two things to happen. Firstly, aj1 equals sum b1 in A again, and at the same time we require it is selected from those already selected, which means there are infinitely many aj. Actually, you could say there are infinitely many aj such that aj1 equals the selected b1 and aj0 equals the selected b0. And you could imagine that continue this procedure, finally what you get. Finally, we're going to subtract a convergent subsequence. Into a bit of the form. Let's call this B. So we will subtract the subsequence convergent to this element, although this is not yet determined, but firstly this is in OF. It's because this is a Cauchy sequence. We don't care what are Bn, but no matter what is Bn, this is element in OF. And we are really just start by looking at the first column. We selected infinitely many, those satisfied, and then when we look at the second term, so maybe sum doesn't satisfy, then we remove it, but there are still infinitely many those satisfied. And then we look at the third term, so maybe there is some term doesn't satisfy here, and then we remove those, but we continue, and there's still infinitely many. So what you could say that, okay, choose your A1J. Let me use a different notation. So I'm selecting from a J, a sub sequence, let's call it A, J, I. No, it's not a good notation. So the J is bigger or equal than 0. A J prime, let's say. J prime is in S, which is a subset of integer. Okay. And so A yeah, why not? So let's just symbolic. This is stupid maybe, but it's just symbolic. So J is still bigger or equal than 0. So A 0 prime, you could choose n to be whatever element from such that, whatever AJ such that its first columns satisfying first coefficient equals B0. So for example, suppose your A0 was satisfying this, and then continue to do what is your A1 prime. Suppose those selecting from those both first and second columns satisfy this. Okay. There are infinitely many, so you just don't choose the same one. For example, let's choose. For example, let's say, suppose A1 doesn't satisfy this, but A3 satisfies this, and then you continue to do this to choose from those such that first, second, third column both satisfy. Suppose this is A7, and you continue to do this. So when you compare this sequence, there are more and more terms coincide with our B here, and finally convergent to B. And as you can see, this necessary, this finite field has cardinality finite. That's why you could always, in each step, find infinitely many terms that coincide with your Bn required. Okay, so this is the proof. So let's come back to the general setting part. So can we see that just what's the minimum setting of this normed field such that it become a DVR, which means maximum idea is local. This is a local ring, and its maximum idea is principal. As the sub-exercise we described, the maximum idea is principal, which means this local ring become discrete valuation ring, if and only if the valuation is discrete. That's coincides with our intuition here. And what makes this a local ring? So actually this is very general. You just have, suppose you have valuation, then this become a local ring because the maximum idea, firstly, all the elements has its norm smaller than 1, forms obviously the maximum idea of all those elements with valuation less equal than 1, which is called the valuation ring or the ring of integers. And why this is the unique maximal idea, I think this is not difficult to prove. So I put this as also some exercise. So let me put 1.5. Or maybe sub exercise 0. It should be put before this exercise 1. You have valuation field. Then the elements f with its norm less than 1 is the only maximal ideal of all f, which is defined to be all those elements with valuation less equal than 1. Let's see, you can even put this elements of f. So this is elements of f whose valuation is less equal than 1.